Oh, so it makes sense. And you're well zoned, so it's not.
All right. So we're hopefully going to be able to finish this method of undetermined coefficients. So we started with this case of constant coefficient. Well, obviously they're all constant coefficient, but constant forcing, so 10. The coefficient in front of the x are always going to be constants for these. And the solution, so we're after the general solution. The general solution describes all possible solutions, not just one. And how you build it is by finding one particular solution and then adding the homogeneous solution. And the homogeneous solution is the solution that satisfies the same differential equation with a 0 on the right-hand side. And last time I only half proved this theorem. So the first part is to verify that the solution that consists of the particular plus the homogeneous added together does indeed solve this differential equation. And that I did. And so we said, say our x is equal to x of p plus x of h. Then you plug it into the left-hand side, and then you end up getting that it does equal f of t. And the x of p and the x of h are the particular and homogeneous solutions. And so the particular solution satisfies the original differential equation with f of t on the right-hand side. And the x of h is the homogeneous solution that satisfies the same differential equation with 0 on the right-hand side. And we use that in this step right here. The other part that you would want to do is, so we know that the sum of the particular and homogeneous solutions does satisfy the differential equation, but can you show that all solutions, so this statement says the general solution of any linear first order differential equation can always be put in this form. So then the other part of the proof is to show that any solution will have this form, and there's no other way of writing it. Or any other way that you write it would be equivalent to this way. So that's the part B, show that any solution to the linear first order differential equation will have this form. And so the way you would prove this is you would say, suppose, so you'll first claim, suppose that x is any solution. So in particular, it satisfies the original differential equation. Okay, so it satisfies this. So we're not saying that x is anything of any particular form. We're just saying, suppose x is any solution, and we're going to write this. So we're going to write x as, it's going to be written as x of p plus some quantity x minus x of p. So we're saying like x of p is the particular solution to this, whatever particular solution we find. X without a subscript is just any solution. And this is a true statement, right? Because we're just saying make it equal the particular solution plus the difference between itself minus the particular solution. And if you distribute, if you drop the parentheses, then you know that x of p minus x of p will just go away. And so this is a true statement. So we're going to make this. And our goal is to show that x will always have to be in this form. So that means that we want to show this is equal to x of h. Because if we are able to successfully show that this is equal to x of h, then we've successfully shown that any solution x can be written as x of p plus x of h. And so what we're going to do is we're going to take this thing that's in the parentheses here, x minus x of p, and we're going to plug it into the differential equation. And we want, like once we plug this x minus x of p into the left-hand side of the equation, in order for this to show that this does equal x of h, what do we want what do we want this to equal? Yes. So that's the goal of this proof. So you're going to say, I'm going to plug x minus x of p into the differential equation. So it's like saying dt of x minus x of p. And then we're going to say plus e of t times the same thing. Okay. Now we're going to do the linearity of different derivative operators. So that means this d dt distributes to each of these. So it's be dx over dt minus dxp over dt. And then the p of t distributes to each of these. So p of t times x. This is a minus, so it's going to be minus p of t x of p. And I'm going to rearrange. So I'm going to say dx over dt plus the p of t times x. And then I'm going to do minus quantity d of x of p over dt plus pt x of p. Right, this is still true, right? I just moved terms around and then I distributed a minus sign because this x of p derivative and then this pt x of p both have a negative. And also remember that this is still true, so I'll copy it from the top here, but this right here, the particular solution satisfies the original differential equation. So this purple statement here is still true for our x of p, so I'll put that here. So this is still true. So given this, again, we're supposing x is any solution to this differential equation. So in particular, it must satisfy this blue thing. So that means dx over dt plus p of t times x. This has to equal f of t based on this blue box. And then based on this purple box, this has to be equal to f of t as well. So you have f of t minus f of t, which is equal to 0. So we saw that if you plug in this quantity in the parentheses, we get on the left-hand side, we end up getting this is equal to 0. So we have this conclusion here, right? We have this is equal to this. So what does this mean? This means, just use orange then. So I always use orange for the homogeneous problem. So we've shown this. So what does this mean? i.e., this quantity x minus x of p solves homogeneous equation. So this x minus x of p solves a homogeneous equation. Therefore, x minus x of p must have been the homogeneous solution x of h. Right? So then we've successfully done what we wanted to do. We've verified that this solution, this x that doesn't have a subscript, we're just saying is any solution. And we're just saying that that could be written as x of p plus x minus x of p because the x of p can go away. But then this quantity in parentheses does actually satisfy the homogeneous equation. So it is actually x of h. So this is equal to x of p plus x of h. And so we have successfully shown that any solution can be written in this form. And then usually, so the two parts of this proof first starts to, you want to just check that this does actually satisfy the differential equation. So we just plugged it in. So show that this does equal f of t using these, because these are assumptions that we're making about what x of p and x of h are. And then we want to show that any solution must be of this form. And so we said propose X without a subscript is any solution. We suppose this, and then we write this in this clever way. And then this thing that's in the parentheses, we show must have satisfied the homogeneous equation, and therefore it is the homogeneous solution. And so it's the sum of X of P plus the homogeneous solution. And so, and then usually you people write like a little box at the end of a proof. So that's the proof to show that this theorem. So this theorem says the form of the general solution for a first, well, actually it doesn't, well, it'll be true for any order differential equation, not just first order, is always of the form of the particular solution plus the homogeneous solution. And that will give you the full, like, general infinite family of solutions. It'll contain the arbitrary constant C, and it characterizes not just one particular, but all the general solutions. Okay. So that's the theory. Now let's go back into the mechanics of how to find the solution. Turns out that the homogeneous solution is always super easy, because I think last time we also did like this problem here where we saw that anytime you have a first order differential equation with constant coefficient, the solution for the homogeneous is C times E to the, if this was a plus K, then it would be minus KT. So that's easy. So the only part that's new or potentially confusing is to find the particular solution. And so for the constant, and that's always going to depend on what's on your right-hand side. So the right-hand side is often called the forcing function, or the input. And so if you have constant input, then your proposed solution form will be a constant. If your forcing function is exponential, then your particular solution will be the same exponential. So this is a e to the t. This one, we thought might be a e to the 3t. Obviously, it has to be the same exponential, because that's the only way you're going to have any hope of having the left-hand side generate something that's going to resemble the right-hand side. It's because you're going to plug this into the left-hand side and you take the derivative of e to the 3t. And then if you plug it into this x, that's the only way you're going to get e to the 3t on the left and have any hope of it equaling the right-hand side. But the issue with this was you get like a so-called meltdown where you get this false statement. There's no way you can find capital A. And we had to multiply by t, and then that required us to do a product rule, but it actually gave us a nice number for capital A that solves, that can force this particular solution to satisfy this differential equation. And there are two things that justify why so first is this solution form is incorrect, because it actually doesn't give us any way of solving for capital A, and it also gives us a false statement. But it also had no hope of satisfying this non-homogeneous differential equation, non-homogeneous meaning that there's non-zero right-hand side, because if you solve the homogeneous problem for the homogeneous solution, we see that it actually is this same form. And so if this, with any arbitrary capital C, solves this equation with a 0 on the right-hand side, then there's no hope that this would have satisfied this original differential equation. Now I want to justify why there's a multiplication by t. So it will always be that you need to multiply this by t if you have these are negatives of each other. So you have a coefficient in front of the x here, and the coefficient in front of the t on the exponential. If those are negatives of each other, then you will always need to multiply by t to the original initial. So it's just this t right here to the initial solution form for the particular solution. And I guess you can already, if you read a little bit down, you'll probably be able to see. But if I wanted to verify this, what would be a good way to verify? What other like techniques do we have in our arsenal for trying to solve a differential equation that's first order? Yes, integrating factor. So remember, we're just doing method of undetermined coefficients for this special case where the coefficient in front of this x is constant. But we did say that the integrating factor works as well. It's just more work. And it not only works for constant coefficient x, but it also works for non-constant coefficient x. So it's the more general method. So if you were going to learn only one method, then the integrating factor method would be more powerful, because it actually does all that the method of undetermined coefficients can do, plus more because it also does it for a non-constant coefficient in front of the x. So we're going to see, okay, well, why don't we just go back and do the integrating factor on an equation of this form and see if the t does naturally show up as the part of the particular solution. And so what I'm going to do is not just even do it for this case where you have -3 and 8 here, but I'm going to just write a general first order differential equation, let dx over dt. And I'm going to say, instead of actual numbers, I'm going to keep it general. So I'm going to say this is k is equal to capital A e to the, so when do we have an issue is if the coefficient in front of this x, which is a plus k right now, is a minus kt right here. This, when these are negatives of each other, is when we're going to have issues. And so we're going to look at that specific case. So, of course, this is negatives of each other. And we're going to use this integrating factor. So the integrating factor says that you're going to say u is equal to e integral of p of t dt. And the p is equal to the k. So just have e integral of k dt. And the k is a constant, right? So k is just a constant. That's the whole point of this, is we're just looking at k's being constants. So you could pull it out. What's the derivative of dt? It's just t, so it's going to be e k t. Okay, we're just dropping the integration constant because we just need one integrating factor. And we're going to multiply this whole thing by this u being the e to the kt. I'll just write it as e to the kt. So if you do that, then the left-hand side becomes e to the kt dx over dt. Then this multiplies as well, e to the, I'll write the k in the front, and then e to the kt times kx is equal to, what's really nice about the right-hand side is e to the negative kt, and this e to the positive kt canceling, just have a. And this left-hand side, assuming that you computed the integrating factor correctly, will always be the t derivative of the product of the integrating factor e to the kt times x. This will always be the case. So this will always be equal to ux, u being this. You could just look at it and see, right? It's like saying multiply the first times the derivative of the second plus derivative of the first times the second. So this is good. And this is still a on this side. And then you can just take the integral. So you just take the integral. And the derivative and the integral cancel. So you just have on this side just the ekt times x. This side is just going to be the integral of a, which is a constant. A is, so we're assuming that k and a are constants. So I'll write that down. And so we're just going to get a t. There's an integration constant that I just consolidate on the right-hand side. And so we just divide both sides by e to the kt, which I'm just going to say is equivalent to multiplying by e to the negative kt. So then the first term becomes at e to the negative kt, plus this term becomes c e to the negative kt. So remember, the c showed up first. So the c also gets multiplied by e to the negative kt. And that's the solution using the integrating factor. And you clearly can see, so the integrating factor will give you each of the particular and homogeneous solutions will be obvious. So from the form of this, it's clear that this looks like the homogeneous solution because it has the c. This is x of h. And it looks like this is your particular solution, x sub p. And that particular solution does contain this t. So you need to include this. As confirmed by the integrating factor. Okay. So and what's really nice about this is it actually gives you like the full solution like in general. So if we go back and look up here, the solution to this, if you're just using this, this is almost like a general formula, right, for the solution now. So if you look at the problem we just had up here, the solution would be, so what is K up in the problem up here? And what is A? So the K, this I actually flipped the sign, so this was plus K. So this is minus 3. So that means that K must have been -3. The A is the capital A that's out here, must have been 8. So if you just use this formula, that just means that your solution should be 8. It's black. Because I'm using capital A times T, so it'd be 8. T e to the, so it's -3, so negative K is, so it's going to be positive 3t plus C e to the positive 3t. And we can just copy and paste this and go back up. Or actually, I don't even have to copy and paste it. It's like clear, right? So if you notice, these two are the same. So integrating factor works. It shows up that t needs to be there. This extra factor t needs to be there in the particular solution. You could also use the method of undetermined coefficients up here, and but you'll have to just multiply by t, include this additional factor of t. So that verifies the fact that you have to multiply by t using the integrating factor. Okay. So so now we're going to move on to a right-hand side that is a polynomial. This is a 1-degree polynomial. Degree 1 polynomial. And for this one, you're going to propose your particular solution to be, so this is a degree 1 polynomial, so we're going to think that it's also going to be a degree 1 polynomial. Why does that make sense? If you plug in this polynomial into the left-hand side, the derivative will reduce it by 1 degree. So a degree 1 polynomial plugged into this derivative will become just a constant. I mean, it'll just be a capital A sub 1, right? And then if you plug it into this x, well, it's just going to be another degree 1 polynomial. So on the left-hand side, you're going to have, in general, a constant plus a degree 1 polynomial, which is in general a degree 1 polynomial. And that, if we can make sure has the right coefficients, has hope of making it equal the right-hand side is also a degree 1 polynomial. So we do need a degree 1 polynomial, like if we plugged in, let's suppose if we plugged in, like in the past, we had like just plugging in a constant. So if we had like, if we just plugged in, just a sub 0. So we don't have the a sub 1 term, but just the a sub 0 term. This is not going to be enough, because if you plug this into the left-hand side, well, the derivative of a constant is 0. So dx over dt would be 0. And then you'll have 2 times a sub 0. And that's just a constant term. There's no t term on the left-hand side, so there's no way you can get this left-hand side to resemble the right-hand side, right? You were trying to come up with a form of a solution that, if you plug in, will satisfy the differential equation, which means the left and the right-hand side equal each other. So this is not good enough. You have to go up an additional degree, so you do need the first degree. And it's really like if you have a first degree polynomial on the right, you do want to plug in a first degree polynomial. You might ask, what about if we had a higher degree polynomial? So x of p is equal to a2 t squared plus a1 t plus a naught. This, if you plug into the dx over dt, will reduce it by 1 degree, and you'll get a 1 degree polynomial. If you plug this into the x, it'll stay as a second degree polynomial. And so in general, you'll have a second degree polynomial on the left equaling a first degree polynomial on the right. It seems like, it's not a good thing to do that, but it's actually not bad, because what'll happen is in the process of forcing this thing by plugging it into the differential equation and forcing it to satisfy the differential equation, you'll find out that a2 will equal 0, or you'll make the conclusion that a2 must equal 0, because there are going to be terms like there's going to be a single a2 times t squared term on the left-hand side, and you're going to just be like, well, there is no t squared term on the right-hand side, so that a2 must have been 0. So if it's going to be 0 anyways, might as well not even have that term and just have only these two terms. So while this is technically going to work, it's just putting yourself through more work. So you want to just maybe minimize that and just do this, but you definitely cannot just plug in a constant, because then you don't have any t terms on the left-hand side that match with the t term on the right-hand side. So we're using this. So the method of undetermined cushion, it's kind of a little bit like some people find it a little unsatisfying, because it's almost like you're just guessing a solution form. But it's an educated guess. So you're just saying, oh, I think this has hope of solving the differential equation. It's a good form for the particular solution up to some coefficients. I'm going to still figure out what those A1s and A naughts, and, if this was a secondary polynomial, it'd be A2s or whatever. But I have a good intuition that this actually has hope of making the left-hand side resemble the right-hand side. And I just have to do some algebra to figure out those coefficients must be to force it to satisfy it. So it is kind of like guessing, but it is like, it's like an educated guess. You're just using your knowledge of calculus to propose what are good solution forms. And so if you're using this, x of p is equal to a1t plus a naught. Okay, we think this is a good form for the satisfying this differential equation. We're going to force it. So we're going to say, I'm going to do some algebra and force it to actually satisfy this differential equation, and some calculus as well, because I'm going to take the derivative of this. Derivative of this is just a1. The derivative of a naught is 0. And then you're going to add this to 2 times the solution that we're proposing, which is this. And we want this to equal 2t plus 1. So we're going to distribute and write terms so I'm just going to order the terms. So the 2 times a1t I'm going to write that first, because I want to write the t terms first. And then I'm going to have plus a1, and then there's a 2 times a naught. And this is going to equal your 2t plus 1. And I want the left-hand side to match with the right-hand side. And so there's going to be matching terms that I'm going to do. So I need this orange thing to match with this orange thing. And then I need this red, like both of these. So basically, why is it not writing? Oh. Both of these. Both means a1 plus a2 a naught, or a1 plus 2 a naught. Those are the 2 constant terms on the left have to add up to 1. So you just do that. So the first one's easy, because it's just saying that 2a1 has to equal 2, which means that a1 has to equal 1. So we got that. And the other one is saying that a1 plus 2a naught has to equal 1. We can use the result we had gotten for a1. So a1 is equal to 1. So that means that you have 1 plus 2a naught is equal to 1. So the 1 minus 1, so this is just going to be 2a naught is equal to 0, because the 1 subtract on both sides. So therefore your a naught ends up being equal to 0. So the a naught's actually going to go away. So our particular solution is going to have, so our A1 was equal to 1. So I'll just say this is equal to this A1 is equal to 1. This A naught was equal to 0. So in conclusion, our particular solution is equal to just t, because it's just 1 times t. And you could check this. So you could check that x of p equals t works. Just take the derivative of t, and that's just 1 plus 2t. That's the left-hand side. And the right-hand side is this. So that does work, right? So plugging in t. I mean, maybe you could have stared at this long enough and been like, well, if I want this left-hand side to look like 2t plus 1, then I can just say x is equal to t. Then this 2t will come up. And then what's really nice is the derivative of t is also 1. So that works out. But systematically, this is how you would do it. You would say, I have a first-degree polynomial on the right. My calculus intuition says that for there to be hope of my left-hand side resembling my right-hand side, I want also a first-degree polynomial. I cannot go lower than that. I could go higher than that, but then if I do that, then I'm going to have a two-term coefficients that I know going to have no t-squared terms on the right-hand side it matches with, so you're just going to make those equal to 0 anyways. And then you do the algebra to find what your undetermined coefficients. So these A1s and A naughts are your so-called undetermined coefficients, and you're just doing algebra to find those. And so, you don't have to stare at this and just have a moment of inspiration. You can just work through the mechanics and then it'll find itself. And that's it. You just have that plus the homogeneous solution. So your conclusion is that your solution is going to be your particular solution plus the c e to the, this is a 2x here. So it's going to be minus 2t. And that's going to be your general solution, which has both the particular solution and your homogeneous solution. Okay. All right. So, yes.
What's the specific form of
So there are a bunch of cases we're going through. We've done, this is the third case. This works if you have a polynomial on the right-hand side. See this 2t plus 1, that's a polynomial. Then your particular solution will be the same degree polynomial. If you have an exponential on the right-hand side, then your particular solution will be the same exponential. So if this is e to the t, then it will also be e to the t with some unknown coefficient in front that you're going to have to force you're going to find that will force it to satisfy. In this case, it happens to be -4. However, if the coefficient in front of the x and the coefficient of the t on the exponential are negatives of each other, then you need to include this t. And in this case, it's e to the 3t, so you have e to the 3t. Okay. And then the very first case we saw was if you had a constant. So if you just had 10, then your particular solution will also be just a constant. But you could think of this as like a subcase of the polynomial case. So 10 is a degree 0 polynomial. And so your proposed solution form is a degree 0 polynomial, which is a fancy word for saying constant. So in a way, this is just a subcase of a polynomial case. I guess there's only two cases then. So let's do another polynomial. This I just added like this morning. I don't know if you've been downloading the blank slides, but I just woke up this morning and added a couple things. I added this page, which was to verify that any solutions, because I was sleeping last night and was like, I don't think I fully proved this correctly. So there's the second part that I needed to add here, but I also added this problem here because this is a confusion that people make sometimes. What did I do? So what's the difference between the one that we just did? It's really just, I just dropped the +1. So you see there's a +1 in the one that we just did. And then it's the same left-hand side, and the 2t is still there, but I ended up dropping the +1, okay? And that makes a difference. It's a quite common to sort of like, okay, so this one the right-hand side is 2t plus 1. So you're like, okay, I'm going to have a general first degree polynomial, a1t plus a naught. This one doesn't have a plus 1, but even if it doesn't have a plus 1, it's still a degree 1 polynomial, right? It's, this is still a degree 1 polynomial. It just has a 0 for the constant term. It's still a degree 1 polynomial. And so you need to, your general solution, your particular solution form has to be a general degree 1 polynomial. What is a general degree 1 polynomial? It needs to have both the the linear term, which is your a1t, plus your a naught. So you still need this a naught. So even though your right-hand side, I dropped the plus 1, you still need this, still include the a naught, which is the constant term. So it's like you have a degree 1 polynomial on the right-hand side, your particular solution should always still be the general first degree polynomial, inclusive of, in this case, the a naught term, even though there is no constant term on the right-hand side here. And I'll demonstrate like what'll happen if you forget to do that, but let's use this and plug it in. So the rest is going to be the similar. I'm going to plug it in. If you plug this in, of course, the derivative of a1t is just a1, and then derivative a naught is 0. Plus 2 times, this is the same thing that we had before on the left-hand side. The only thing that changed was the right-hand side is just now 2t. So then you're going to say that this is just 2a1t plus a1 plus a2a naught is equal to 2t. I'm just rearranging so that it's in the right order. So this has to match with this. And this red thing has to just vanish, right? So what we need is, I'll use green. So we definitely have to have this orange thing, which is that the 2a1 has to equal 2. So that means that your a1 has to equal 1, which is the same as what we had before. But you also need this to just simply go away. So you need this because there is nothing, no constant term on this side. So you just need this whole green thing to just go away. It needs to vanish, be equal to 0. But we also know that the a1 is equal to 1, so we could plug that in here. So you'll get 1 plus 2a naught is equal to 0. And if you move the 1 to the other side, it's -1, but then divide, so a naught will equal -½ Okay, so last time your a naught was 0. So last time we had a plus 1 here, and then we proposed the same solution form, the general first degree polynomial, and in the process discovered that a naught was 0. So we didn't have a constant term in our particular solution. This time I dropped the constant term on the right-hand side. We still propose the general solution, general first degree polynomial, and the a naught is actually non-zero in this case. So we have actually, like, you can't just drop this a naught because it actually wasn't 0. And so we get that a1 is equal to 1 and a naught is equal to -½ So our solution is just going to be equal to t minus a half. So that's because 1 times t and then minus ½ plus the homogeneous solution is the same as we had before. So it's going to be the e to the -2t that we had. So our particular solution is this. Our homogeneous solution is still this. Right? So what if you forgot to include this a naught term? So you just looked at this right-hand side, you saw 2t. Okay, so the particular solution will also be like a times t or something like that without the a naught. So what if you forgot? What if you forgot the A naught. Or I'll just say, what if you forgot the undetermined or constant? Undetermined coefficient. Okay, so that means you're saying that the particular solution is just going to be A times T. A times T without any other constant term that gets added to this. Okay, let's plug this in. The derivative of A times T is just A, plus you'll have 2 times AT is equal to 2T. Okay, so you got a couple things you need to happen. We need, again, the T terms to match. So these two have to match. And you also need this term to go away. So what does this mean? This means that from here, we know that we need to have 2A is equal to 2, which means that A is equal to 1. But we also see that there are no constant terms on this right-hand side. So that means we need this to equal 0. So what's the issue? We get A is equal to 0. We also get that A is equal to 1. These are different. Which means we cannot find the capital A. There's only one coefficient here, so that works. And by that observation, this is not going to be sufficient for this. It's common for some people to just think that you can just solve for capital A. So this is also a common mistake. So I want to make sure that I maybe say something about it. So some people say, okay, well, why don't I just solve for capital A without, assuming that it's a constant. So then you'll just say, I can distribute the capital A and then say it's 1 plus 2T is equal to 2T. And then you say A is equal to 2T over 1 plus 2T, right? So you're like, okay, I found A that would actually force this thing to be true. We're just assuming now that A is not a constant. Now that's actually not allowed because when you plugged in this solution form, just remove the red so that we can see. When you plugged in this x of p equals A times t, we got that the derivative dx over dt is equal to A. What assumption did we make in that? That A was constant. So it'd be wrong for you to say, I'm making the solution, we're proposing the solution form as capital A times t, where capital A is a constant. I'm going to plug it into the differential equation. So I know that the derivative of A times t is just A. And then you're going to renege on that or go backwards on that and then say, well, let's just not assume that A is a constant anymore and then solve for A and you get like, this is definitely not a constant, 2t over 1 plus 2t. You're contradicting yourself. So you're doing one thing and then now you're saying something else after that. So this is not allowed. All of our method of undetermined coefficients you're plugging in assumes that these coefficients are constants because in the process of plugging into the left-hand side, all your derivatives, you're computing, assuming capital A or capital A1 or A naught or all those are constants. So you're going to have to keep that assumption all the way through in your algebra to solve for the A naughts and A1s and potentially A2s and A3s. You can't just suddenly say, well, I made that assumption there, but now I'm just going to assume that it's not a constant and just directly solve for capital A, right? So you have to do this matching term thing. And there's definitely no way you can get this left-hand side, assuming capital A is a constant, to equal just 2t. And so you do need to have a general first-degree polynomial. So just general first-degree polynomial will work. The idea is that this has not enough degrees of freedom. So what I mean by degree of freedom means that this only has one thing you can tune. Capital A is the only thing you can tune. This has two things you can tune. You can tune A1 and A naught. So it's more general and it has the, more general means that it's more it may be more possible to force it to satisfy. So there's more freedom, degrees of freedom to make this work out. All right, so I was hoping I could get to all of this, but I ended up talking too much. So we'll do the sinusoidal input, which is the last case. Like that means the right-hand side is a sinusoidal function like cosine. And then we're gonna do something that combines two forcing functions. So you have exponential plus a sinusoidal. So this is like two things on the right-hand side. So there's something called the superposition principle, which I'll prove, and we'll just use that. And then once we're done with that, we're gonna just go into like actual word problems because I think that's enough for math and just move on to applications. But I have office hours tonight it's like at 5, I think. So if you guys need help, so have a good day.